analysis for instrumented bridges. Okay, the particular structure that we're talking about is the Samoa bridge located in the Northern California. This bridge is got 22 supports, including abutment 1 all the way to abutment 22, and it's got 20 columns supported on very massive pile foundation and pile caps. The bridge is about a little bit over 2,500 foot long, and the width of the bridge is 34 feet wide, which is a two-lane bridge with 4-foot shoulder on each side. So this is the schematic view of the bridge. This is a rendering that I've done with Midas, full 3D option in a Midas. You can see the superstructure is composed of a composite deck, including the pre-stress post-tension 4 beams with the supported on hexagonal columns. Like I said, massive pile cap, including this photo, which is from the rendering of the Midas, shows the pile caps, including existing piles and retrofitted piles. It's a very complicated structure as far as doing the analysis. As you can see here, you got combination of vertical piles with different diameter. Also, you have these smaller diameter piles which are battered and so forth. This is all included in details in the Midas 3D model. So let me tell you what happened when you look at a seismic analysis of these long span bridges, and what are the steps and process that you have to go through in order to be able to analyze these type of structures. First, when you have these long span structures, obviously the ground motion at every support is going to be different. So first, engineering seismologists will develop a rock motion at every support. The motion will be propagated using the side response, coming to the foundation level from the geotechnical engineer. So far here is the rock motion will be done by the seismologist. Geotechnical engineers will use some type of a shape type of analysis, propagate the motion, bring it to the foundation level. Structure engineer will shape the structure and come up with the response of the structure. Now this response is a function of time. It could be moment versus time, it could be shear versus time, it could be displacement versus time, and then based on this response we will design the structure or superstructure and the columns and the foundation. But what do we do as far as instrumentation for this type of structures? Not only we put instrumentation at the superstructure at the foundation level and at the columns, but also we put instrument at depth, various depth within the ground, so we can also measure the free field ground motion. Because obviously, no matter how good of a structure model you develop, if you don't have the good ground motion and foundation springs, your model is not good. Therefore, we want to see how we can record ground motion even within the ground, so we can calibrate our computational and computer models for the free field motion. So, like I said, we put instrument on the bridge and at various steps within the ground to get the recorded motion. This is one of the bridges that we have done instrumentation. This is, as a matter of fact, the Antioch bridge. It's been recently retrofitted. We have base isolation. And the advantage of using base isolation, therefore you limit the force that goes to the column and goes to the foundation. Now, as you can see from this photo, the pile caps are very massive. Therefore, you have to include them in your structured model. Here is another example of an instrumented bridge. You can see again, the pile caps are very massive, and therefore they need to be included as part of your foundation and the superstructure model, and that's why we need to use computer programs such as Midas and other computer programs that have the capability of doing a direct model, which means including the piles, pile caps, superstructure within the model. And I will explain it as we go further along. So this is an example of instrumentation. That is a seismic instrument located at top of the bank cap in one of the bridges, which is also sitting on the base isolation. So this is an example of instrumentation from the superstructure. We also have instrumentation sitting at the top of the pile caps or at the bottom of the columns. Also, as I said before, we have instrumentation within the ground. I've taken this picture actually looking at top of the bridge and looking down. These are instrumented location within the depth, varying depth in the ground. So for example, this might be at 50 feet, this might be at 300 feet, and so forth, and this might be at 1,000 feet deep in the ground. So we can also record the free field motion during the earthquakes. This is a particular structure that we're going to be discussing today. Is a picture of the Samoa bridge. And this bridge has got instrumentation. One of the particular instrumentation is actually located at this pier, which is called Pier 8. And we have instrumentation at the top of the bridge. You might actually be the snapshot of it right around here. And also we have instrumentation sitting at the top of the pile caps and also within the piles. So here is a schematic cartoon that I've drawn for the Samoa Bridge foundation system at Pier 8 that we were talking about. This particular slide actually is for this pier right here. So you can see that the piles are at the pile cap is not at the mud line. The piles are in this particular location, the piles are about 40 feet into the ground, and they're about 50 feet cantilever above the mud line, all the way to the water surface, which you can see here. So these piles are actually almost like a cantilever sitting on pile caps, and pile caps is above water surface. The soil within the vicinity of the piles are acting very nonlinear, and away from the piles, basically they act linear. We're not going to get to the discussion of linear, nonlinear soil. That might be for another discussion for maybe a future webinar, which we are actually using a near field, far field analysis also in Midas, but I will discuss that in probably subsequent webinars. So here is a schematic drawing or a snapshot of pier number 8 from Midas, trying to replicate this cartoon. So you can see the soil is actually about 40 feet into the piles are about 40 feet into the ground, and then the cantilevers, and you can see clearly here this is done in detail in Midas 3D. So as you can see here, the soil stops here, and then the remaining portion of the pile foundation system is cantilever with the pile cap and the superstructure. So the soil is where I have this circular line drawing. These are actually nodes representing the soil springs, which we will discuss later on. Now, let me give you a little background how we develop these foundation springs, regardless of it is a complicated long span bridge or these typical simple bridges. This is a bridge that also has been instrumented in the Southern California, has been shaken by many earthquakes, and we have seismic instrumentation at various locations of the bridge. As you can see here, these are all seismic instrumentation. Now, the reason I'm showing this picture is not actually discussing this bridge, but I'm trying to show you that modeling of the bridge is important, and is important to model all the components of the bridge, which we call resisting component for seismic. So you can see we have abutment, which is soil. We have to convert this soil into springs, and these are nonlinear springs. We have the superstructure, and then you have the columns, the pile cap, and the foundation, including a nonlinear soil element. And also you can see here, I got springs in the longitudinal direction, as well as the transverse direction, which represent the shear keys and the lateral resistance of the soil in the abutment. So here is the backfill, and this is the column and foundation springs. So how do we develop the spring for the abutment? This is from a research that I have done, and also is in Caltrans SDC now. In order to model the foundation, the abutment springs, we use this very simple equation. It's very simple. This can be done in a minute Excel now. So Fy, which is a force displacement relationship for the abutment backfill. Now the reason I'm showing this slide here because I use this very same slide in order to model the abutment for the model I used for Samoa Bridge in Midas. So here is how you calculate the abutment spring. Basically a constant C times Y, which is a displacement in the longitudinal direction of the bridge, divided by 1 plus D, another constant times Y, which again is the displacement in the longitudinal of the bridge, and the constant C and D, very easy to calculate. You use an average stiffness from the soil and ultimate capacity of the soil to calculate constant C and D. If it's a cohesionless soil, which is a sandy soil, the maximum PY is 0.05 H. H is the depth of the bridge or the height of the back wall. So very simple calculation. And if it's a cohesive soil, like clay type of material, Y max is 0.1 times H, which basically would be, it takes a lot more displacement to mobilize to get to the F ultimate. Now this F ultimate calculation is very simple. Either a geotechnical engineer will give it to you, or you can use this classical earth pressure theories to calculate the passive pressure. And that's how you develop the nonlinear springs for the abutment in the longitudinal direction. According to the Caltrans STC, we even simplified this a lot more. We're just saying, okay, ultimate capacity would be 5 KSF, and K for sand, it would be 50 kips per inch per foot of wall, and for clay, it would be half of it. So it takes less than a minute to calculate from the nonlinear abutment springs or elastoplastic abutment spring. Very simple. All you got to use just these two numbers. The reason I'm showing you this because it really doesn't take too much to develop a good model once you already know how the boundary conditions are to be set. So I've also developed a very simple equation. This has actually been published already. If you want to develop a nonlinear springs, all you have to do, if you don't want to use those coefficients, is A times Y divided by 1 plus 3Y H to the power 1.5. That would develop this nonlinear backbone curve. Remember, I had the constant C and D, C in the numerator, D in the denominator, based on experimental data that we have, and we have done many, many full-scale experimental tests. I came up with this simple equation. So in order to develop the abutment springs, maximum it should take you is 1 minute. All you got to do, type this in Excel, A times Y divided by 1 plus 3Y, and you set up the Y maximum to be 0.05 times height of the abutment. That's all you have to do. You develop your nonlinear abutment springs. But of course, many abutments, they also have gap. Now, here is a trick. In the finite element model, you can either use a gap element, then put the nonlinear springs, or make the gap element or the gap as part of your backbone curve. Another way, your abutment spring would be flat, and then it goes to a nonlinear. Then you don't have to use a gap element in the finite element model, because once you develop a gap element and you want to use time history, it takes a longer time to find the right solution. But if you put a gap as part of your backbone, it'll be done in no time. The computer program doesn't know this is a gap element. It just takes it as a backbone, part of your backbone curve. So that's how you develop the backbone for the abutment. Now, for the pile, in order to develop nonlinear spring for the piles, you basically stick a pile in the ground, and based on the different source layer, you apply a load or a force or a displacement, and you come up with a deformed shape of the pile, and as a result, you develop this nonlinear abutment springs, pile springs. Now, if you need to linearize the foundation at a given displacement, then you need to come up with a linear stiffness. So another way, this is a deformed, this line is a deformed shape of the piles. Based on the deformed shape of the pile, you can linearize the springs. And then you can put a linear spring along the pile in your finite element model. Or you can use non-linear spring in the finite element model. What I have done in the current model I'm going to show you in Midas, I did not linearize anything. Just like the abutments, I use a full nonlinear springs along the pile in the finite element model by Midas. Okay, and this is, I just put this slide as a reference in case if those of you are interested in to see how I calculate the nonlinear spring. I use a Reese sand model. And I just put this as a reference to show you what I did for develop the foundation springs. Reese sand model, you can Google this, or if you need more information, send me an email. I will basically give you more information on how the springs are developed. But I use the sand Reese model to develop nonlinear spring along the piles. Okay, so now, so far we talked about how, see, the boundary condition of the model is extremely important. Therefore, you need to be able to develop the correct boundary condition for the abutments and a correct boundary condition for the pile foundation. The boundary condition of the abutment, I showed you how it's developed, very simple equation, which are based on experimental data. And the pile springs, I use a Reese sand to develop the nonlinear pile springs. Now let's talk about 3D soil foundation structure interaction methods. So SFSI stands for soil foundation structure interaction. We have what we call a substructure method or a direct method. Substructure method, we separate the foundation from the superstructure as if the foundation doesn't exist, and we model the entire foundation by soil springs. It's an iterative process. It is not as good as using a direct method. In the direct method, we model the foundation, the soil, the column, and the superstructure as one entity. It would be basically a direct model. We put everything as is in the model. Now, the reason we go for substructure model, because many computer programs, they don't have the capability to run as fast, therefore we use substructure. However, nowadays, if the computer solution is fast, you better use a direct method, better model the foundation and the superstructure as one model, which I have done with Midas. So in a substructure model, basically you model your foundation as a 6x6 stiffness matrix, a mass matrix, and a damping matrix, and you come up with what we call a kinematic motion for seismic. In other words, you ignore the foundation by replacing it with a 6x6 matrix at the bottom of the column and some type of a seismic excitation as your input motion, which we call a kinematic motion. And this is the process that we use. So you model the foundation separate, in a separate computer program, completely separate, and come up with a 6x6 matrix. And you basically model the foundation, you push the foundation to come up with or the pile to come up with a deformed shape. And as you come up with a deformed shape, as a function of deformed shape, you put a 6x6 matrix at every node. Because remember, this is an element which has a 60-degree freedom at each node. And the foundation springs are linearized and incorporated into the 6x6 matrix at the element. And then you condense all of this foundation, including all the 6x6 matrices, to a 6x6 matrix at the bottom of the column. So that will replace all your foundation to a 6x6 matrix, so you don't have to worry about breach foundation. And that's how you linearize, again, as a function of displacement of the piles, you linearize your springs, these nonlinear springs at displacement 1, 2, 3, for example, which displacement 1, 2, 3. And then you incorporate it into your substructure model. If you do a direct model, you don't have to do this. You don't have to worry about all this. All of this nonlinear spring will be part of your foundation model, and part of the superstructure model. And this is what I've done in Midas, which, to be honest with you, it is the first time that I attempted to do this. I was very hesitant to do this. I thought it's going to take forever to do, and I'm not going to be able to do it. But I was able to do this with Midas. and the run time was done in less than 4 hours actually. I was very surprised. And then to develop the kinematic motion as part of the substructure, like I said, you input your free field motion at every node and shake the foundation to come up what we call a kinematic motion. It is this kinematic motion and a 6x6 matrix that will replace the foundation and not to include it in the global bridge model. Like I said, if you do a direct model now, you don't have to do any of this. The global model will do this already as part of the global model of the structure. So, and that's how you have to go a lot of trouble to develop 6x6 matrix for substructure model. Another way, here is a foundation model. You need to develop a 6x6 stiffness matrix, a mass matrix, and a damping matrix. Now, to develop the damping matrix, we use a Rayleigh damping. You need to, basically, you already, from this step here, you have a 6x6 stiffness matrix and a mass matrix, and then you go to Rayleigh damping by using alpha and beta. You have the mass and the K matrix. You develop your foundation damping matrix. Now, typically when you design a structure, you use 5% damping. However, because foundation has a lot more than 5% damping, typically for foundation, at least you need to use about 10% damping for this value zeta here when you solve for the C matrix. Now, so that's how you develop your damping matrix. You already have the mass matrix, you have the K matrix, you use alpha beta, Rayleigh damping to calculate the 6x6 also damping matrix. So if you want to do substructure model, you have to do all this to develop substructure model. You have to develop a 6x6 foundation matrix, damping matrix, mass matrix to develop a substructure model. And it's an iterative process because the stiffnesses are developed for a given displacement. We don't know what kind of displacement we're talking about. That is the drawback in the substructure model, that you have to guesstimate a stiffness based on a given displacement and go back and forth until you converge to a stiffness that you like when you look at the global model. And all the substructure in model can also be done in Midas. You can input your 6x6 mass matrix, stiffness matrix, and damping matrix. Midas, I thought there was a webinar already explained this 6x6 stiffness mass matrix and so forth implemented in Midas. I think there was a webinar already explained how you do this in Midas. Okay, now, so this is what you do. If you look at the global model now, you have your foundation 6x6 matrices, which include the mass matrix, damping matrix, and stiffness matrix, and then kinematic motion, which foundation is done, model for foundation is done separately. So you develop, using the substructure method, you develop these matrices, including kinematic motion, and then model the structure as if there is no foundation. And like I said, this is very painful. You have to go so many iterations until you make sure that the superstructure and foundation displacement are compatible. So here is an example of the substructure, which I've also done with Midas with this project. This is a closer shot of one of the main piers at Midas, which I use a kinematic motion and a 6x6 matrix also to develop the model. And here is the direct model. All the piles, including the nonlinear PY or springs, including the spring in the transverse direction and the longitudinal direction, are all done in one model. You can see all the battered piles, retrofit piles versus existing piles. They're all included in the model. The superstructure is shell. Nonlinear abutment springs are attached at the tail end of both ends. And like I said, the nonlinear springs, as you can see here, are also attached to the pile foundation. This is a schematic cross-section of the bridge, which is 34 feet. It's about 4 pre-stressed beam. And it's about 2,500 feet is the length of the bridge. The detailed model, this is a snapshot of the Midas model also. You can see the beams here with the diaphragm in between. These are also included in the Midas model. This diaphragm also, this is a snapshot of the Midas model. So again, now we're looking at a schematic of the instrumentation on the bridge. We have a seismic instrument at the bottom of the Pier 8, which is right here. We have instrumentation at the top of the pile cap, bottom of the column. We have instrumentation also at the superstructure. These are all the channels. For example, channel 5 and 6 are at Pier number 4, channel 10, 11, 12, 13, and so forth. They're at Pier 8 and so forth throughout the structure. Now, as an engineer, before you do any analysis, you need to step back, look at the schematic of the bridge and see what you really should expect from your analysis. What you think you're going to do that makes sense when you run the analysis. If I look at the schematic of this diagram here, you can see some of the pile caps are buried into the soil. And then starting at Pier number 14, the piles are cantilevered above the mud line and support a massive pile cap. So when I do my analysis, any action that I should see are really in this zone, because most of this is very stiff, but here is where I have the cantilever, where I have massive structure, and all the actions should be happening in this zone. And as I'm going to show later on at the ADI from Midas, you can see actually how this model represents reality. And I will be comparing the analytical model versus recorded motion at the pile cap and at the superstructure. So here is another rendering of the closer shot of the Midas. You can see these are nonlinear springs attached at the tip and along the pile. Just because there is not enough space to show all the springs, I just put some springs as a schematic representation of the nonlinear springs. But all these nodes, you can see all these lines, they all have a 3-component springs attached to them in the longitudinal direction, in both longitudinal and in the transverse direction, as well as the vertical direction, which is called PY, and this called TZ, and at the tip, we call them a QZ curves. So they are all incorporated in the model, including massive pile cap and the superstructure. Another closer shot of the Midas, looking at even a gap, the drop span. That span is about 225 feet is the length of the span. It's about 30 feet of cantilever, and it's about 165 feet is the length of the what we call a drop span at the main channel. This is the main channel, and I have instrumentation at the piles, at the pile tip, top of the pile, and at the superstructure. This is so when I make the comparison in the analysis, I'm making comparison at the recorded motion at this main channel Pier 8. So here is more schematic drawing of the Midas model again, with the nonlinear springs, with 225 feet is the length, and so forth. This is a suspension span, and the typical length of other spans are about 120 feet long. So again, we're looking at a schematic drawing of the Midas model versus a real bridge. So that is a main span that we're talking about. Instrumentation is here, which is in Midas model. We're looking at it right there. Now, the pile caps are very massive. This is actually part of the retrofit that we were doing. The retrofit actually was done in early 2000. Here is a pile cap which is very massive with the pile foundation. For this type of a structure, the modeling of the pile cap, correct modeling, correct dimension, correct mass of the pile cap is extremely important because it's a dynamic system and mass comes into play. So it is very important to make sure you include the pile cap mass and, if you can, the pile foundation as part of your global system. So all the mass participation will come as real as possible. Again, nonlinear springs, closer shot of the piles. These are nonlinear springs attached in Midas. One thing about the new version of the Midas, I don't know for those of you who are using Midas if you have the latest version or not, but you can basically develop your nonlinear springs outside Midas and copy paste them in Midas. It has a new option now that you can develop your nonlinear springs, tension and compression, and easily copy paste them in Midas and then attach at every node. You can attach those springs very easily. Again, closer shot of existing pile versus a retrofit piles here. This is superstructure is modeled with shell. That's another thing. I thought if I'm going to use shell as a superstructure, it's going to take forever to run the model, but I was very surprised that even with shell element, and not just a beam element for the superstructure, the model, I was able to run the model very fast. This is a view of another downhole array. These are basically recorded motion. We have recorded motion at close to one of the abutment embankment. This is going over the bridge. So these instrumentation are not attached to the bridge, but at some depth within the ground, so we can record free field motion. This is basically as you can see, at various depths. We have instrumentation. We have instrumentation all the way from 125 meters, at 50 meters, 25 meters, and at the surface, so we can record the motion at various depths and also at the surface. Now, these are not the motion that is going to basically shake the structure directly. We fit these motions through nonlinear springs attached to the piles, and then we shake the bridge. And if you do a substructure, you need to come up with a kinematic motion, which is none of this motion. That means you really have to model the foundation separately using this motion and come up with a kinematic motion. But if you use a direct motion, no problem. Just attach this motion to the springs and structure will take, the finite element model will take care of the rest for you. So here is another schematic of the main pier. Very complicated structure. These existing column or piles are hollow. Then we have the retrofitted piles, which are 60 inches in diameter, existing are 54 inches diameter hollow. The column was retrofitted also, which there's not enough time to really explain all these. But we have a recorded motion. Channel 9 and channel 11 are in the longitudinal direction of the bridge. Channel 8 and channel 10 are in the transverse direction of the bridge. And of course, channel 7 is in the vertical direction of the bridge. So I do have a paper. I send it to Midas. You may request, they will probably send it to you, which shows all the comparison between these using the Midas model versus the recorded motion. You can probably ask Midas to email you the paper. So these are the recorded motion in the longitudinal direction of the bridge. I'm looking at basically channel 11, which is the longitudinal direction, and channel 9, and free field motion, which is at somewhere at the base of the column or at the base of the piles. So the black line is a recorded motion, and which is channel 31, free field. Channel 9 and channel 11 are recorded motion at the bottom of the column and top of the superstructure. Now, looking at the recorded motion, especially if you look at channel 9 and channel 11, it appears that, first of all, they move in phase, and it appears that we almost have a rigid motion at the bottom of the column and the top of the superstructure. That means it pretty much moved in phase. That's in the longitudinal direction. In the transverse direction, same thing. You have a recorded motion, which is a free field motion somewhere at the bottom of the piles, and then recorded motion in the transverse direction, which is channel 8 and channel 10. It seems the column and the superstructure move very much in phase. keep in mind, the pile cap is very rigid. So it is no surprise that they have moved in phase. This is, by the way, from an earthquake in 2010, earthquake January 2010, magnitude 6.5. So now what about the analytical model versus the recorded motion? So I'm looking at analytical model channel 11 in the longitudinal direction, which is top of the superstructure versus the input motion. The kind of reddish line is the input motion in Midas, which is recorded input motion. The black line is the Midas result versus the bluish, which is the recorded motion. So, of course, this is a preliminary result, and you can see how nicely we were able to match the Pile's biggest displacement at a right location, and it pretty much followed the same trend, even though we're not at the tail end at some location, we're not matching, but the main thing is that we were able to match the largest displacement of the recorded motion versus analytical model in the longitudinal direction. Let me see. This is a recorded motion in the transverse direction channel 10, which is located right at this location at the top of the superstructure. This reddish line is the recorded input motion, which I used to shake the Midas model, and of course the bluish is the recorded motion. Now it's interesting also to know that if you look at the two peak of the recorded motion, peak to peak, and if you look at the period of the structure, which is peak to peak, basically will give you the predominant period of the structure, is about 1.48 seconds. And the number I get from Midas fundamental period in the transverse direction is 1.46 seconds. That's what I got from Midas. And if you look at the recorded motion, is about 1.48 seconds. So now the question is, well, how could you get such a perfect match? Of course, I have the recorded motion. You start your model, and then you start getting the model as real as you can. Initially, I was getting about 2.2 seconds as my fundamental period. Then I noticed that I don't have the correct mass in the for the pile cap. So I modified the model such that I have a correct mass for the pile cap. I start getting a better period, and then I still was not able to get 1.48 seconds, and then I ended up using a crack moment of inertia, I crack for the columns. Once I got the I crack for the columns, then I was able to get 1.48, 1.46 seconds for the predominant period in the transverse direction of the model for the main span. Of course, this is a very complicated model. You don't expect the whole structure to move in phase in a transverse or in the longitudinal direction, but in the longitudinal direction, the predominant period is about close to a second, and I was able also to match the longitudinal period of the model versus the recorded motion material. So here is a direct model using Midas. All the nonlinear springs are attached, and you can see all the actions actually are at the main channel, as was expected by looking at the schematic drawing of this profile. So this is a direct model, nonlinear springs, everything is attached, and shot of the model, just getting closer shot at Pier 8. This is where we have the instrumentation actually. You can see how the drop span actually is moving. When we looked at the acceleration record of the breach, we saw a lot of spikes at this location, and when you look at the model, you can see actually how this span is hitting this two cantilever portion, and that's one of the reasons we're getting a lot of spikes in the recorded motion, which I don't have it here, or for the interest of time, I didn't show it here. Now, I have developed this model actually yesterday. I was working on this model. Since I had the model of the superstructure, I've decided to also develop a substructure model. And with the substructure model, I put my 6x6 stiffness matrix, damping matrix, and a mass matrix at every location here, and shook the superstructure or the model to see what we're getting. I was very surprised actually. I was getting very good result also, but the interesting part was this model ran in 1 hour and 2 minutes. The entire model ran in 1 hour and 2 minutes. So here is the AVI of the substructure model. And in this AVI, I've used the undeformed shape, so you can see relatively how the bridge actually is moving. Of course, these are exaggerated AVI scale, high scale AVI, just to show you the concept. But with the new application of the Midas, I don't know if you guys have the latest version, you can easily implement a 6x6 matrix, a damping matrix, and a mass matrix at the bottom of the foundation or the bottom of the pile cap or the column, depending on what your references are. Or in this model, substructure model, I have decided to keep the pile cap because it's very massive, and put the mass of the piles in my 6x6 mass matrix. But I kept the pile cap because it's very massive. In my model. I'm pretty much done with my presentation. So I guess with this, that's all I have to say. If there is any question, I don't know how much time we have. I'll be happy to answer any questions. If not, if you have any question, you can always send them to me, send them to Midas, they'll forward it to me, and I'll be happy to reply to all your questions.